Welcome to this video. I'm going to present a presentation we did for Riscure in our user workshop. It's about hacking the RHMA contest. We will see some demos, but it will be with very cheap hardware so that everybody can do it at home. What we're going to do in this video, first I'm going to explain a little introduction about what is the Riscure Hack Me challenge. After that, we will see how to break an AES implementation. That was one of the challenges that we had in this embedded contest. Then we will see how to bypass a password implementation. So there was something here, it's a check, and we will see how could we glitch it in theory and in practice. Before we start, so why I wanted to show this video, this small presentation, is because when this contest was run, I had quite some excuses of not participating. Like site analysis equipment is very expensive, or there are super advanced attacks and this is out of my reach, or it will not work on this. Okay, so this kind of made me sad, and that is the motivation of this presentation. You will see that with very low-end equipment, you can still do these attacks. So let me start with an introduction to this Riscure Hack Me challenge. So this board that it's here connected, this was an embedded board. It's based on an Arduino Nano version 3 board. This was the Riscure Hack Me 2 challenge. It was a capture the flag type contest, and there were a lot of participants all over the world, more than 500 participants from 49 countries. More than 400 scored. The maximum score was 5,700 points, and 30 teams scored more than 850 points. That means they solved several challenges. And something to know, there will be a Riscure Hack Me 3 challenge. The pre-qualification part has finished already, but if you're interested, please contact us. Maybe we can make some board available for you. You have the website, you have also our Twitter account, also printed in the screen. This year, the contest will be themed in an automotive fashion. So we partnered with Argo Securities for some challenges that look like if you were attacking an automotive ECU or an automotive component. So if you're interested, please join. So, piece of advice before we show the attacks. Please don't get me wrong. What we're going to show here about breaking crypto, it's not about breaking the crypto itself. To date, the crypto systems we're going to see here, they are not broken by mathematical attacks, by pen and paper. What we're going to do is bypass it. We're going to see some sidetrack that we can get the keys in an interesting manner. So, let's start with the first session. The rules of the game, for everybody to be able to reproduce attacks at home, is that I am very constrained with what I can do for hardware. I am going to use the cheapest I could find when I started this presentation, so I just Googled online what is the cheapest. This should be generic for any target, so what we're going to see here does not apply only for the Riscure Hack Me challenge, it applies for any target. It's going to use only open source software. So here, although in Riscure we have professional tooling for doing these things, I am going to only see these with open source. And these results, you can reproduce it at home. So just clicking, it will work if you have such a setup. If not, you will see that it requires minimal effort to modify the scripts. So let's start with the first challenge. As I said, we're going to do an AES implementation bypass. We're going to start the keys of an AES implementation. Let's see what it was, the challenge. This challenge, if you look at the Riscure GitHub account, you can download it for this board. It's called piece of SCA key or piece of cake. The goal is to extract an AES key from this device, and the info we get is that this device, when we send a message, it will return this message encrypted. Okay, so this is all we know. We send a command to this device, it will encrypt a message with AES, and we will get back the ciphertext. So, how does site analysis work in theory when we do an evaluation? The first thing that happens, we have to measure the power consumption of this device. Once we have some power measurement based on this AES computation, we typically have to do some signal processing. Then, once we have processed the signal, so we have the interesting part, we have to verify that this is actually a crypto process. We are not measuring just garbage noise. And if this turns to be some crypto, if there is leakage of this crypto data, then we can perform an attack. Here, if it's an evaluation lab, you would make a report, and the goal of this report is to assess how strong is a device. If we have an attacker profile, it's exactly the same process. The only difference is that you don't make a report, you just extract the key and then make use of it. So let's look step by step what are the steps for such analysis a bit more in depth. How can we measure power? Then, how do I get traces? Traces is these power recordings. It's always the same setup. In this case, I have the computer I have here for the presentation. I'm also going to use it for acquiring power measurements. Then we are going to talk to this device. So this device has a serial interface, a UART interface. We're going to send commands, we get a response. Okay, so this part, it's already implemented in the device. We also need to measure power. For this part, I'm going to explain in a second a bit more in detail how it's done, but this we could use a resistor or some current probe or some sensor that allows us to measure the power. And we need some digitalization part, like a digital oscilloscope. Okay, I will explain in a second what is this one. Once we have this input-output data and the power measurement, then we will put everything together in a computer and we will compute this attack called a side channel attack. It's called DPA, but moreover in a second. And this attack, this workflow, it's done for any target. Okay? Communication, power recording, and analysis. How do we measure these traces? What is the setup that I have here? So here I have the USB cable, and what I've done in the USB cable is I cut it and I've put here a small resistor in between in series. Then if you do that, you can measure what is the voltage drop of the resistor, and because I know what is the value of the resistor, then I can compute how much power is going, because I can compute what is the current. What is the problem of such an approach is that here typically for a good measurement, you need to tune the resistor. If it's very small, it could happen that the resistor explodes because too much current. If it's very big, it could happen also that the chip does not get enough power, so it doesn't boot. So let's assume that it works, that is properly set. Then here you have the formula that we can use to compute what is the power going to the target. And for your knowledge, there are many more ways to measure power than just a resistor. So you can use current probes, you can use electromagnetic measurements. So all of this is possible, but we're not going to see this today. The main reason is because if you remember, we had very, very low budgets. And here, a resistor is very, very cheap. It's 5 cents. If it's a really good resistor, typically it's 1 cent or even less. Okay, so we have a resistor. We can measure power. How does it work in practice? So here you have a picture of what is the setup. What I have here in this little board is the following. I have here my serial cable. So this, I did not use the serial cable on the board. I used an external cable that costs €3. The reason is because I removed the chip. Here I also have a resistor. So this resistor is the thing I'm going to use to measure the power that goes into the board. Okay. And here I have an oscilloscope. This is the cheapest I could find. And how it's going to work is as follows. I'm going to record the voltage drop over the resistor. So one of these probes is connected to the resistor. And I'm going to also measure the activity of one of the LEDs of the board. When this device is active, there is a LED that blinks to show that there is activity. Most IoT devices or USB devices have this blinky LED. Let's go to the computer and see how it looks. Okay, so here I have in the computer a script. The first thing I have to do is I have to initialize the scope, because this scope is so low end that it does not even store the configuration. I have to reprogram every time I want to use it. As you can see here, this oscilloscope now it's listed. It says it has 2 channels. So here I'm going to now start a script. Let me show it first, the source code. So here, this script, what it does is the following. I configure some parameters, like how many samples, or in other words, how much time I want to record, what is the measurement speed or the sampling rate. Then I have here some parameters to store the data in some folder. I set up here what is the communication speed for the serial interface, and then what I do is, in a loop, the following. You can see here that starts iteration. I do the following. I get some random bytes, then these random bytes are sent to the serial interface, and at the same time, I am starting here a capture from the oscilloscope of what is the power in the two channels. Okay? So this SIGROC toolkit, it's an open source software that you can use. And what happens is I send the communication to the device, I start the capture, I could sleep for a while if I have to keep some time for recording. And then I get two things. I get the response from the device, and I also get what is the measurement. Okay? And I repeat this process a lot of times. If I run this, you will see that this is how it looks. Okay? I have the power measurement, which is started in parallel to the communication, and I have what is the input message, it's a random string, and what is the output message, it's another random string. It is actually not a random string, it's the encrypted version of this input string. Okay? So in this case, we took 10 measurements, it took 8 seconds. Typically for an attack, we would need something like 1,000 or 2,000 for a device which is not protected like this one. Let's take a look now at what did I capture. Okay? So I'm going to open a previously captured measurement. Pulse View is another tool from the same open source initiative. Okay, let me zoom into the trace. And this is what happened. So here you can see in channel 1, we have some measurement. I'm going to zoom a bit in so that you see it better resolution. And I have in channel 2 this measurement that looks like a flat line. What is this? Here, the second line is connected to this blinky LED. So here we can see that when the device became busy, it turns high because the LED is on. In the other channel, which is the resistor, you can see that here we have some sort of repetitive pattern. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 patterns. And these patterns start to appear when this busy LED is on. Now, if you're familiar with crypto, then you would realize that the AES encryption scheme uses 10 rounds of an AES encryption round. So it's basically repeating 10 times the same process. In Power, you can already see here that we have 10 patterns. So most likely what they've captured here is the execution of this encryption, this AES process. Okay. So this is what we have to capture many times with random data so that we can compute statistics, and with these statistics we can retrieve what is the secret key. So this is the power measurement. As a recap, we have the oscilloscope, we have a resistor, we are sending data, we get the data back, but also the power consumption during this computation of the encryption. What is the cost of such a setup? Resistor in this case, it's 5 cents of a euro. You can also get it with 1 cent or even cheaper. The cable, the USB cable, is something I took from a trash can, so it's free. I also used a USB soldering iron for removing some of the decoupling capacitors. So here in the board I removed the filtering part to have a very clean power track. I don't have any filter. So for this I use a USB soldering iron. This I bought off internet from China. It was 7 euros. Okay, if you don't want to use it, you can leave the capacitors, you need more traces, but it still will work. I also used this oscilloscope. Well, it's a digitizer, let's call it like that. It's the cheapest I could find. It does not support hardware triggering, so everything is done by software. But still, as you will see, even with such a cheap device, this attack will succeed. Okay? If you're thinking of investing a bit of money in a scope, do not buy such a low-end oscilloscope. Buy something that at least supports hardware triggering, because it will make your attack much easier. But this is just to prove the point that even with such a low budget, you can work. You also need this RHME board, which is an Arduino Nano board. So you can also get an Arduino Nano and program it with the challenge. Total hardware cost, 55 euros. So this is way, way, way cheaper than any setups I've seen here in internet, like, yeah, this is too expensive, an oscilloscope. Well, a second-hand oscilloscope, like a proper one, you can buy with less than 200 euros, and it's much better than this. But even if you have 50 euros, you can still work with this. So we have the measurements. What is the next step? Signal processing. How do I improve the signal? In this case, we are going to give this a miss, because here we don't have enough time in this short video to show how to do signal processing. This is a very broad topic, but there are plenty of open source and dedicated tools to do this. You can use Riscure Inspector, you can use open source initiatives like Octave, or statistic tools like R or Python, NumPy. There is a lot of stuff there, so just browse internet signal processing. There is also a toolkit that we're going to use later called Julia SCA. This also even includes some signal processing techniques like alignment that you can follow the tutorials on Julia SCA. It's on the Riscure GitHub account, it's open source, you can use it. The most important thing is that this board has a LED, and this LED always starts blinking when we start the process. So this is actually a perfect signal to start aligning all the process. Okay? How to do this in real life? Well, here I have another script. Let me show it. Okay, 1 second. So here, this script, it's already set for this demo, how many traces I have, what is the length I capture, the triggers threshold. But basically here you only would need to fill in the parameters. And with these parameters, what this script does is the following. It will read the input-output from the file. It will read the capture from this SIGROC toolkit, so basically the data from the oscilloscope. And it is a very, very, very simple Python script, which what it does is looks for where is this start mark, this trigger. It will verify that this is happening in the middle of the measurement, not very early or very late, because that would mean that we are too late or too early with the measurement. And if it can find the start mark, then we keep a chunk of the data. Okay. If you run this, you will see that now the tool will start finding this start mark. This is called the trigger. Okay, and this, well, basically after some time it will be done and it will output a collection of traces. This later will be processed. Okay, so I'm going to leave this working in the background and continue the presentation. The third step, leakage detection. So how does this work? Is this device leaking? So for this there is a methodology called TVLA, Test Vector Leakage Assessment. And this methodology, the only question it answers is there leakage? Is this secret leaking somehow or not? Okay? This attack or this methodology does not extract the key. This only allows us to know if we can succeed with the attack or it's not likely to succeed. How does TVLA work? It works as follows. You have to acquire two sets of measurements, group A and group B. What could be A and B? It's two types of measurements which are statistically different. What do I mean by that? One set could be always the same message, constant input. Another would be random input, random messages. I would expect that the power consumption for always constant message is different than the power consumption for random messages. There should be some variation change. Okay. Once we have these two groups defined, then we apply statistics. There is a statistical approach called the Welch t-test, and this test, what it results is the following. If there is a high value of the t-test value, that means that group A and group B are different. In other words, that means that I can tell apart if I am using a constant text or random text for input. In other words, I can see in the power measurements that there is some dependency depending on which data I am using. This means I can apply a statistical attack to extract the key, because I can infer from the power measurements what is happening. Was the data constant? What is random? This we can see. Okay. So in this case, because this, I would need to set up again the measurement and start these two groups and compute these t-tests, for example, with NumPy or any mathematical toolkit. I'm going to use a tool called Riscure Inspector. Okay. This is the professional tool we have, but this we could use with any open source tooling. Okay. Okay, so this is the measurement I just showed before, these patterns. And then I am going to compute this t-test. Okay, this is quite a fast test, it takes seconds to compute. And then we expect that if there is a spike over 4.5, that means that we are 99.999% sure that there is leakage. Here, if you can see the line, this yellow-red line is 4.5. The spikes here in the medium of the crypto is more than 100 and something. So if we look here, the highest peak, this seems to be 97 standard deviations. So in this case, this you could also compute with open source software. But basically, if we go to the question, does this board leak? Yes, it does leak, and it leaks a lot. Okay, so that is why we can use any sort of open source tooling. Okay. So for this attack, you can use a constant versus a random text. If you know the key, you can apply a non-specific test like a semi-constant versus random and yields better results. This is the attack I specifically use here, but you can do this perfectly with open source tools. For the last part, how do we perform the attack for such analysis? How do we extract the key as an attacker and we make profit? So this is how such analysis works. On the one hand, we have here the target. What I know is the messages I send to it, and I know that this device is doing AES, so it takes my input, computes some intermediate values, some rounds of AES, and gives me back the output. However, since I can also measure the power, I have the actual power leakage. Okay, so in reality, as you can see in the slides in the left, we have the message, an operation with the real key that I don't know, but I can measure the power consumption. As an attacker, what I can do is the following. I know AES, how the crypto works, it's a standard. So if I know the input, I can make a guess of the key. I can make a hypothesis. With this hypothesis, then I can say, if I have this message and I have this input or this possible key, this should be the intermediate values. This should be what would happen in the AES. So I can make an estimation of how much power I'm using. And this is what we're going to do for the attack. I have the actual power consumption, the actual message, and I'm going to make a hypothesis of what could be the key. If I have a hypothesis of the key, I can recompute part of this AES. And I can compute the distance between my guess and reality. Are these power measurements similar to my estimations of power? Yes. Then that means that my key guess is right. In other words, I have the successful attack. How does this work? For comparison, we can use something called correlation. This is what is used in an attack called differential power analysis. We have the data that happens inside this AES, and we can make an estimation of power. For example, if I have more ones, then I should use more power. If I have more zeros, I should use less power. This model is called the Hamming weight model. So here you can see in the slides what is the data, what are these Hamming weight values according to this data. And then I do the following. I take the first point in time of these power measurements, and I take these data points. I take the Hamming weight of it. And with these two data sets, I compute the Pearson's correlation coefficient. I see if these two things move in synchrony, if they have a dependency. Okay, this is a mathematical formula, and it will yield that result. And I do this for this data and every single point in time. Here in the slide you can see that in the middle of this power measurement, if I have Hamming weight high, the power is high. If I have Hamming weight low for a given trace, then the power measurement is low. So in the middle of the crypto, there is a dependency. This is interesting because now I can detect where in my power measurements I am using a certain data. This does not yield the key. This just tells me where the data is used. how does it work if I want to apply this for an attack? Then for an attack, what you do is the following. This is a scheme on how AES works. What I'm going to do is I'm going to use known data, and I'm going to attack a certain part of the algorithm that uses the key. For example, it could be the first round, this add round key or sub bytes operation. We could also do this from the output. It doesn't matter. As long as I start from a known point, I will make a hypothesis of the key and I will compute these intermediate values. First, I'm going to run the attack for you to see how it looks. Okay. So I'm going to go back to these open source tools. And here, what I'm going to run is this Julia toolkit. Okay. So this Julia SCA toolkit, it's an open source toolkit, which is actually found also in the Riscure GitHub. It's mainly contributed by Kees Barbrunes, one of our principal analysts in Riscure. And here, what I'm passing as a parameter is this collection of power measurements I just processed to capture where it starts. Okay. What the computer is going to do now is the following. The computer is first going to parse this data, and then it's going to make the following assumption. I have the input data, and I have the first part of the key, let's say it's 0. Then I compute for each measurement with a given input data what would be the intermediate state of AES. And I'm going to compare that to the power measurements. Then I'm going to take the second byte of the key, I'm going to take the input data, and I'm going to compute what will be intermediate values for the second byte. Okay? And I'm going to try this for the different possibilities. If I do this for every key byte, then there will be one possibility for every key byte that seems to match better reality than the rest. And this is what you can see here in the slides. If I compute correlation for different key possibilities, there are some key possibilities, like for example 32 for the last key byte. There is one always that is much more likely, there is much more correlation than the rest. It matches better what happens in reality than the rest. So if this happens for every single key byte, if one guess is better than the rest, then the result is that you can get the key. Okay? So in here you can see that this is the recovered key, and actually this was verified because after we get the key we can encrypt the input to get the output. Okay. And this is how a SCA attack works. Let me present the same thing with slides so that it becomes clear what happened. So we know the input, this was the message that we give to the device. And if we know the SBox input, so what happened to the SBox's the secret part where we mangle the key, we would also know the key. But the key is not possible to retrieve it. Okay? Because the AES encryption, what it does is it confounds, it merges the key to the device, it merges the key to the intermediate value, so we cannot unbind them. Because we cannot undo the cipher, there are many rounds and we cannot revert the procedure, then what we're going to do is the following. We're going to take one of these SBoxes, one of these key bytes, and I'm going to make a guess. Let's say it's 0. If it's 0, then these SBox functions are public. Then I can compute what will be the output for a given input. And these are the values, this SBox output, that I'm going to use for correlation. Imagine that for a certain key value, like let's say 0.3, I have that this correlation spikes. So what does it mean? It means that these SBox outputs are happening. In other words, that means that my guess was matching reality in these intermediate values. So in other words, I know 8 bits of this key. If we do this attack now 16 times, once for each one of the key bytes, then you get the full AES key. How many attempts does it mean in reality? This means we have to do this 256 times per key byte. We have 16 key bytes in this case, it's AES 128-bit, so that means 4096 attempts in total. Okay, so this is quite fast, it takes seconds as you saw in the exercise. So let's summarize what happened. In the end, here we have built a setup that allowed us to measure power consumption, and we also were able to run this side channel attack called TPA, differential power analysis. And here we only used open source tooling. In this case, when I used inspector was just to show that there is leakage, but this step you can completely skip and just it will break the same. This, as you can see in the attack, it was not used. Then here, the cost of this attack, how much was it? Well, for this setup, it was 55 euros. Perhaps when you're seeing this video, this will be much less because you might find something cheaper. What about time? This took me 1.8 days to build the setup because this scope, the open source driver, had some bugs and I had to fix it for the input range, and also I had to interface the toolkit. But once I had the setup up and running, then it took me minutes to do this capture, and the open source software for DPA, I used one of the tutorials and this works out of the box. What was the result? I could retrieve the full key. Okay, so this happened because this device, this challenge was not thought with security in mind. And this happens, unfortunately, for many devices that if they don't have security microprocessors or they don't have security in the design process, it's relatively easy to break them. The second takeaway is that here, building such a setup, I did not do excessive coding. I just wrote a couple of Python scripts and then everything was working. So the security here, it's in this device non-existent. The open source tooling is getting better and better. So if you have a device that is very weak, you can see that this in seconds you can break it. Okay, so this is something interesting to realize. And for me, I also would recommend that now, if in the new challenges like Riscure Hack Me 3 challenge, you have an ACA challenge, then you build such a setup and you try, because it's much easier than you think. So this was for the first part, for the site analysis part. Let's look now at a different perspective. Let's look at fault injection setups. So this was another challenge. It was called Fiesta. And what was this challenge about? So here the only information we were given is the following. The goal is to unlock the device when we load this challenge. And what you can see if you connect to the device is the following. You see that the device boots, it prints a string, and then it keeps printing in the screen lock, lock, lock. It prints this string forever. So then when we start an attack, then the first thing we make is a hypothesis. What could be happening in this device? So this was my hypothesis. I thought that the code in this board looks something like the slide. I have some flag, some variable, which is locked or unlocked. In this case, it's not unlocked, so it's unlock false. Then it bootstraps the board. It prints this boot string. And then there is some sort of infinite loop that keeps printing this lock, 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 lock thing. So here, if you have to inject a fault or a glitch, what would you glitch? So here, by injecting faults, we can change data, or we can also change the software flow. Because here, with a computational fault, if it's on the instructions, then you execute something different. But if, for example, I corrupt the unlocked flag, I might turn it into true. What can be attacked here? Well, there are many, many, many things that could be attacked. For example, change the value of the flag. I could also try to skip the if statement to print the secret, if there is such a thing. What did I glitch in this setup? This is something important to realize, that for fault injection attackers, it is always an unfair game because you have quite some advantage. A fault injection attacker, the only thing you have to do is, I don't care what I glitch, I just want to print the secret. As a developer, the different ways to attack this thing, there are many ways. You have to protect against everything. Okay, so this is always an unfair game. An attacker needs only one way in. A developer needs to protect everything. Since I didn't care, I just wanted to try to print this secret. The only thing I needed is, how do I inject a fault? If now we have the constraints of I need only open source software, I need the cheapest I could find, then I thought of all possible fault injection attacks, what could be the easiest? One of the easiest, due to hardware requirements, is voltage glitching. Just to cause a spike in the power input and see what happens. In this case, this chip was working at 8 MHz. It could also work at 16 MHz, but it's quite slow for modern standards, so timing should not be an issue. And here, internally, I did a bit of brainstorming for what could be a setup. For example, I could use some sort of microcontroller, and I could use 2 power supplies, and a transistor to switch between them. I could also use a digital to analog converter and some buffer to power this device and then put some DIP. I could use some multiplexer chip and a buffer, so several options. But then I realized that here the goal is to show you that it's possible with the cheapest possible. So I made something I called a cheap glitcher. So here I used a board that we use internally in Riscure for training. It's a ARM Cortex CPU, which works at 168 MHz. And this chip, it's working at 168 MHz. You can drive the general purpose input-output pins at 100 MHz maximum. If you use any other device that works at these speeds, for example, some Raspberry Pi or BeagleBone Black or anything, even an Arduino, you could get similar timings. Okay? We need some current to power the board. In my case, this board that we have internally, each pin sources 25 milliamps. So if I hook up some pins in parallel, I could power this device perfectly. So this is the device I made. What I did is I put some general purpose I/O pins. I'm going to toggle them. And I have a minimum length of 10 nanoseconds. This is way faster than a clock here. Will this work? Well, this is something that I was not sure if it would work. But after some time in the SHA conference that I spent with some colleagues, then I just used this board and I hooked up some wires. You can see that this is not a very beautiful setup. And you can see here the following in the slides. Instead of saying lock, 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 it says chip unlocked. And then it prints some flag. And then what I did is I just reset the chip with my finger. I press the reset button, and you can see that it prints this initial bootstrap flag, and then it prints chip unlocked and flag. Why was that happening? Is because after 5 hours of effort that I just coded in a microcontroller, please toggle these pins, I was 100% successful. I always managed to glitch it at the first attempt. Okay, so this is just a program that toggles one of these pins low for a while. So in this case, this is something that I used internally, this development board. So it was a surprise that I could do this. Could you do this even cheaper? So in this case, I used a development board from ST, this STM32F429 board. This I got from a workshop for free. If you buy it, it's not that expensive, it's way less than 50 euros. So again, I just hook up some wires to the power pins of this device in parallel. And it also works 100% of the time. Okay, so the cost of this board was free. If you had to buy it, it's still way less than 50 euros. Can you do even further? Can you do even cheaper? If you happen to have another of these Riscure Hack-Me boards, the clock speed of this device is enough to produce the glitch that has a 100% success rate for this device. So I didn't try it, it's up to you, but I'm sure you can glitch with one RHME board, another RHME board. Also, just some mention, some people tried, for example, from Hyderabad, they made a custom PCB to do this glitching. Guy also, he tried with a MOSFET and I think an Arduino board, he also glitched it. So basically, almost anything you try will work. The only thing you need is a bit of patience and try the different settings, but if you try, it will work. Okay. Takeaways for fault injection on this RHME. The first thing is, this is a general purpose microcontroller. And in this case, I was able to glitch it successfully 100% of the time. I spent less than 5 hours of effort and with open source things or development boards. Okay, so this is the ST Discovery board was completely unmodified. It was stock. I just wrote a custom program for it. But why is it possible? It is possible because this chip is not meant to be secure against fault injection attacks. Manufacturers, they have a security line of microcontrollers that withstand these things. But if it's a general purpose device, it's for features rich rather than resilient to fault injection. Okay. Also, the coding here was not aware of fault injection. It was not of a defacing coding style. What is the second thing to learn here? Because you have seen that it is possible to glitch things with such low effort, this you have to think of how you write your own code. Because here, I was able to do this very, very simple without any trigger or without any synchronization because this is an infinite loop. Basically, I had 3 retries. I could try to glitch, and in the worst case, if I had a very big glitch, the device resets. But it's an infinite loop, so it's always retrying. It's kind of free. You have to think of your implementation. Do you have such a structure? In the slide you have a code of, for example, a generic secure boot. You verify some signature of the flash, and then if this signature fails, that means that the secure boot chain is broken. You could do two things. You could just stop, or you could just do like this, an infinite loop. If you have an infinite loop, what happens if I have a fault and I skip this instruction? Then I will boot my invalid flash. So as a wrap-up, this Riscure HackMe platform is very useful for learning. Okay, the code is publicly available in the Riscure GitHub account. The code that you have there, it's very useful because it has notation. So if you want to learn how to think as an attacker, you can practice with it. And also because there are so many open source tools, like this Julia toolkit, like this SigRock toolkit, just please try it. And if you learn how to do these attacks, you will learn how to be a good site analysis and fault injection attacker. Also, something to realize is that the homebrew site analysis and fault injection tooling, it's becoming more powerful. So, for example, for SCA, this Julia toolkit is very nice. There are more alternatives like CheapWhisper or these site analysis marbles, so a lot of things. Do not underestimate a low-budget attacker if you are a developer, because you have seen how much effort does it take and how much budget does it take. And something important, if you are thinking of participating in the Riscure HackMe 3 challenge or in other hardware challenges, you can ask us for the code. This will be made publicly available because this is all open source. And I would say try these attacks. Good luck. If you have any question, you can always try to contact us in our email account or in the training academy. And this is it.